Okay, everybody, looks like we're recording. Let me share my screen. Share that one. Okay, carbohydrates and fats. So we've already talked about the digestion and absorption of these guys. And so what we're going to look at now is where they go once they're absorbed. So uh, as we've talked about earlier, and as you've seen in some of the slides, hopefully, carbohydrate is going to be converted into glycogen and stored in the muscle and in the liver. So we're going to look at that. And that becomes important because if we can, the more storage of the fuel we have, right, the longer we can go utilizing that fuel. That becomes important in long races. And in particular, races like triathlons and in marathons. It depends on honestly how fast, right? So like if you're a 5K runner, so you're going a little over 3 miles and you go real slow, you may go long enough to have to utilize, carbohydrates, and carbo loading may be something you do, but the intensity is so low, you're probably not burning through the fuel real fast. So understand that too. It has a lot to do with intensity. Okay, that's how do we know that? Well, let's look. There's an assignment. This don't worry about it in the slides. I haven't pulled this one out yet, but it's in Canvas when that's due. Oh, I don't know why it does this, but anyway, Kropf and Lindart in the 1920s looked at the importance of carbohydrate in exercise, and they wrote a couple of papers on it, and they inspired Levine, Gordon, and Derrick in 1924 to do a glucose test on Boston Marathon runners. So they published in 24, they tested them in 23, found that most were hypoglycemic. In other words, they didn't have any blood sugar in their blood. They didn't have any sugar in their blood after the race, which makes sense to us nowadays, right? Because we're like, well, yeah, of course they're using it to. But back in 1923, this was a new deal, right? It's like, whoa. So they repeated the test the next year and fed them while they ran. So they had along the race, of course, like we do nowadays, they had a stop for these guys that they were testing. And so they, of course, had a control group. So as they ran by, the ones with the, pink ribbon on their shirt or whatever, got to eat something, and then they kept running. Well, they found that not only did they have sugar in their blood after the race, which made sense, they also increased performance. So they were really excited to see this, and most of us should be, right? We should be pretty excited to get that information, right? Wow, we have an advantage now over other people. So Christensen demonstrated that not only was sugar important, but he found that it was really important with intense exercise. So as intensity went up in exercise, carbohydrate utilization went up as well. That's about as far as we got, right? We could test the sugar, but as far as getting a little bit more in depth as to what happens in exercise and what exactly is the mechanics there, the physiology, what was going on, we really couldn't tell. We didn't have the tools until later on. So in the 60s, we had better tools. We actually did muscle biopsies where we took muscle samples from live people, right? And then looked at the myofibril or the muscle cell to see if there was any differences. And then we compared those differences to the sport or to the activity that they did. I actually had a professor who was much older, obviously, when he was teaching me, but in the 60s, when he was a grad student, he took part in these muscle biopsies. He actually muscle biopsied his girlfriend to make sure she was slow twitch muscle fiber. I think I might have told that story in the lecture. And sure enough, she was, and they had two really athletic endurance children. Anyway, Costill and Miller in the 80s began to come up with the recommendations to carbo load because they looked at these muscles. They knew that endurance athletes had a lot of mitochondria. They could store glycogen pretty well. But the idea was if we could get more people to store glycogen, then we could produce more ATP over those longer endurance runs. And that would be really important for performance. So they came up with a plan to store more glycogen through something called carbo loading. Now, that's a pretty common term nowadays. But carbo loading back when they first instituted it was a mess. So we're going to get to that here in a second. So where do we store this glycogen? We store it in the muscle and the liver. This should be kind of a repeat for you. It's stored in the fibril and it's stored in the liver cells. And its main function is to provide energy for muscle contraction. The myofibril doesn't give it up. If it's in the muscle fiber or the myofibril, it's used there. The liver, its main job is to release it back into the bloodstream. So we're going to store 300 or 400 grams in the muscle cell. Depending on how intense your exercise is, it will determine our rate of oxidation. So we have to be really careful. High intensity, we get through it faster. Moderate intensity, a little slower. And I'll show you a graph here in a second. Once again, cells don't give it up. Once it's in the muscle cells, they stay in the muscle cells. So here's a kind of a chart on that. If you look on the vertical column, we have glycogen content. So if we're at 100%, we've fed ourselves, we've allowed it to be stored, and then we begin our activity. Light exercise, it's just sustained for a long, long time. Heavy exercise or intense exercise, think above about 70% of max heart rate. You're going to last just short of 60 minutes. And then moderate exercise, somewhere around 2 hours. Most of your competition is going to be somewhere in between. So we like to think somewhere around 90 minutes. That's in a well-trained individual. So most of us are going to be more towards the 60. So if we're somewhere between, I don't know, 50 and 70%, that's moderate exercise. Anything above 70% or so is heavy exercise of heart rate. So the liver glycogen is about 80 to 100 grams stored there. So once you start depleting muscle glycogen, your blood concentrations of sugars go down. It'll register in your brain that, hey, I need some more blood sugar, and your liver will then secrete its storage. And when does it start to secrete? Well, when you get between 4 and 4.5 millimoles per liter. So that's a concentration level. Okay, and at rest, we can probably last 8 to 12 hours just on our liver stores. So if you eat a big meal before you go to bed, you'll never transition into fat burn, because most of that will come from either stored glycogen in the muscle or your liver will maintain it. Now, if you eat a meal at 6 o'clock and you've performed moderate exercise and now you're going to bed and you've depleted muscle and sugar and you've got a little bit left in your liver, now your sleep, you'll burn fat calories at rest. So you can see how the fuels transition depending on the concentration of glycogen in your liver and in your muscles. This depends a lot on your fitness level and if you're refueling during an event. So how often you eat. If it's depleted, you have to eat a large amount of carbohydrates to restore it. Okay. At about 80% of your VO2 max or somewhere max intensity, so you can think of that as heart rate as well, your liver releases more glucose than your myofibril can take up. The reason for this is because insulin is depleted a little bit, so it can get into your bloodstream, but insulin needs to help it get into your muscle cell. So you're only going to get about 80% effectiveness. So what we don't want to do is rely on the liver again during competition. It might be okay if you're not in competition, but we don't want to rely on it in competition. It drops our max output down. There's always going to be a greater demand by your muscle cells for that blood sugar than what your liver can support after about 60 minutes of exercise or so. So regardless of what you have stored in your liver, there's so much muscle in your body that needs it. It's going to be in debt. So we've got to be really careful not to rely on liver stores. When our muscle cells our storage is done, that's before that even happens, we need to start eating again in order to maintain activity or performance levels. So we don't want to get hypoglycemic. So the idea of carb loading became very important, right? We want to have it stored in the muscle cell so that it's in the muscle cell and we don't have to rely on the liver, and we certainly don't want to transition to fat. So the idea for carb loading was we were going to preload lots of glycogen in hopes that we can provide enough fuel to make ATP through a long event. Understand that this is really difficult to do. I'll show you what it looks like. I'll show you the classic one and the modern one, and then I'll have a huge list of the reasons why it doesn't work very well. True carbo loading lasts 7 days. This is the classical supercompensation protocol. Once again, this is back in 1967, and then in the 80s, they were like, yeah, this works pretty good. And then we found that it didn't work pretty good. It became popular in the 80s, I guess is a better way to put that. So look through how this works, right? So 7 days before your event, you're gonna have a really hard, intense workout and deplete all of you're gonna become hypoglycemic. And those of you who have been low blood sugar know that that's an awful way to feel. And you're gonna do that on purpose, and then you're not going to eat anything to restore those carbohydrates. So for the next 2 days, you're just gonna eat proteins, maybe some fats, and don't do any workouts. That's all you're gonna do. You're just gonna sit around. So remember, this is not just physical, it's psychological too. If you're an athlete getting ready for a big event, the last thing you want to do right before it is just sit around, right? It's just the anxiety of the idea that maybe I'm not going to be prepared, all those things that go through your head. So you're going to do a hard workout, deplete all your stores. You're not going to eat carbohydrates to restore that. And then for 2 days, and then for the 4th day, you're going to do another exhausting workout just in case you did eat something. And then 2 more days of no workouts, and then only high carbs. So I don't know if you guys have ever done that, but there's a lot that goes on when we obviously eat high carbs. Your gastrointestinal tract has to work. It gets real gassy. There's a lot of pressure. There's a lot of movement. So this is really difficult to do too. And then of course the day of the event, eat another high carb meal. So you're, well bloated, and then go run your race. So that's the supercompensation model. There it is in a list. So if somebody says they're going to carbo load for a race, they're either going to do this one or they're going to do the modern day one. And the modern day one is just a slow taper. So basically you're going to taper down your exercise and you're going to taper up your carbohydrate intake. So it's about you're going to go from about 25% carbs, which is fairly normal, to up to 70% towards race day. And that seems to work pretty good. It's a little easier on your body psychologically and physically. So that if you're going to carbo load, the modern day one is more beneficial. And if you look at the numbers, you're getting about the same amount of benefit, which honestly isn't great. So you're going to do a week's worth of work for probably maybe 15 minutes of benefit. So I'm not sure why. Just eat something during your race. Let me repeat that. Just eat something during your race and you don't have to carbo load at all. So if somebody tells you right before your big 5K race, your big 3-mile race, that they're carbo loading, just nod your head and say, okay, it's not the race to carbo load for, and it's not going to help them. So here's the big busy slide that talks about all the reasons why research tells you that why athletes fail when they try to carbo load, and it's just a miserable process. Once again, just eat during your event and you'll be just fine. So once again, there it is. You can read through this. I put it on there so that you always have a little reference as to why carbo loading isn't a great idea. So would you consider it? Maybe, but you'd only consider it for an event that's going to last at high intensity for longer than probably about 90 minutes. This picture here is a picture of a race that I did at Lake Powell. It was an Olympic try. That is not me. I'm not sure who that is, but this is the race. It was obviously a wet day and people crashed their bikes all over the place. Problems with carbo loading. I talked about this already. You can read through the list. Once again, it's just the benefits aren't there, right? You're only getting a small benefit for a lot of work. And unless there's an event that you can think of greater than 90 minutes that you can't eat at all. Maybe a swimming event, long distance, but once again, even the ones that do long distance swimming out in the ocean, open water, they have a boat there and they reach a big pole out and they feed them while they're doing it. So it's not like there's not an opportunity to do it unless you're built that you just can't eat, or your athlete just can't. They get really sick. I don't know. I don't know. All right, so here, what you need to do then, if you're not going to carbo load, you're going to intake food 3 to 5 hours pre-event. That's the ideal. That gives especially if it's right, you're fasting at night when you're asleep. You give it 3 to 5 hours to get completely digested, absorbed, and stored in the muscle. Now, if your race is at 6 a.m., obviously you're not going to get up at 1 in the morning to do this, or 3 in the morning to do this. So what else can you do? So you can also do a 30 to 60 minute intake, but you have to be really careful. If you're going to do 30 to 60 minute intake before your event, so you're an hour away, make sure you don't eat too much carbs, and make sure they're more on the complex meat mid-range ones. And I'll show you how to look that up, because you don't want to spike your insulin. Spiking your insulin will cause you to either crave more sugar, push too much in, or and not allow other like fat to be utilized later on. So if you're going to do the 30 to 60 minutes pre-event, you have to make sure that you're going to eat during the event. So there you go. Regardless of the event, by the way, I mean, anything more than 60 minutes. So 16 to 9. You can use something called the glycemic index. We don't have that textbook available anymore, which is okay. You can do it online. Just type in glycemic index, and basically you're going to see things listed from 0 to 100. So your 100s will be like syrups, right? Your cordials, which are all just like sugar, just straight gel sugar. They digest super, super fast. They're your disaccharide, monosaccharides that are in a gel form, and they get absorbed super fast. Mid-range on the glycemic index are the ones that are a little bit more complex. They take a little longer to break down. And then, of course, your single digits and 20 on the glycemic index are going to be your really complex carbohydrates. The reason why you want to know that, right, is you want to be able to stretch. One of the ways you can time your fuel input is to give something more complex that takes a little longer to digest, and that way it gives you a little longer of a race at max effort. So as you're pushing into that 45 minutes and you have complex carbohydrates that are still being absorbed, and there's enzyme action still taking place, that will slow down the absorption rate and allow you to utilize it a little bit at a time instead of all at once. So it's kind of nice to know. Now we're going to do a project during the semester called the Barkley. There's an event in Tennessee called the Barkley Marathons, and you'll watch the video. It's on YouTube. It's one of your assignments, and take good notes. You want to look at the products that they eat when you're watching the film, see what those athletes are eating, and then try to determine where it is on the glycemic index and why they're doing it. Like when they're drinking cans of Coca-Cola, right? They're getting a stimulant because they're not sleeping, and they're also getting really fast sugars because they're going right back out on the course. So it's an interesting movie. If you haven't seen it, it's a documentary. I apologize. There's a couple of bad words in it if you're opposed to bad words. So anyway, there's your glycemic index. Pre-event, 30 to 60 minutes. Use low GI. In other words, 30 to 60 minutes out, you're going to use sugars that are a little lower, not 50 and below. During the event, you're going to use something higher, 60 and above, so it uptakes quicker. And then post-event, you're going to mix both. Now, of course, we haven't mentioned proteins, which is fine, but this is just the carbs. That's a pretty good statement of how you should ingest them pre, during, and after your event. Anything you eat during your event is considered exogenesis. You want to start early. So after about 60 minutes, you're way behind, right? You're already you've started a process that's not going to allow you to get back your potential very quickly. So you really do want to time it so that every half an hour or so in a long event that you're eating something. Now, for an event, usually it's around 7 grams an hour is pretty good, right? Because it's not so much that it's going to spike your insulin. It's just enough to keep your muscles fed. So if you cut that in half, you're going to go with about 3.5 grams every half an hour. And if you think about it that way, it's about 3 of those or 4 of those little fruit snacks. That's not much to carry around. So you can carry some fruit snacks with you, or whatever you like to eat. That'll give you about 3.5 grams every half an hour, or 7 grams an hour. For recovery, you want to eat within an hour of exercise. It should be within the hour, and I don't mean like, okay, wait an hour. Within the hour. So if you've ever done a long race, you see that they have like this picture, like tables full of bananas and oranges and I've even seen nuts out there and crackers and granola bars. We had one race. Matter of fact, it was the race I showed the picture. Lake Powell, they did honey buttered bread. Oh, it was wonderful. So make sure that you're getting those carbs in first, and then your proteins can come in as well. You cannot use proteins without some source of energy, and those carbs provide that energy to help with that protein synthesis. So make sure you're getting those carbohydrates on board for recovery. Once 3 to 4 hours later, you can eat stuff lower on the glycemic index, and that's fine. But get something high so you get it on board and get your brain functioning again, those muscles working, and prep your body to start using amino acids for protein synthesis. Fat oxidation kind of runs the same way. It's a fuel. However, it's not efficient for exercise, not as efficient as carbs anyway. While we sleep, it's usually most of our energy requirements are met by fat oxidation or fat burn. And it's interesting, when we first start exercise, when we first start a race or we first start our workout, we get a boost in lipolysis. So research shows us that we actually get a little bump in fat burn, which is interesting. It's like our body's prepping to lose our carbohydrates. So it's saying, okay, we got to start the process, because fat oxidation takes a while. That's why it's inefficient. It takes longer to break it down in order to get it to use in the Krebs cycle to produce ATP, which allows muscle contraction. So it gets a little bump. But then when the intensity goes up, fat loses its ability to keep up. And so then you need the carbs. So once you get into past about 60% of your max heart rate or max effort, your fat utilization goes way, way, way down, and you really are reliant on carbohydrates. So, of course, the longer the event goes, right, the longer the duration, the more fat oxidation we have, because now the longer you go, we tend to slow down, right, and then we're in that heart rate zone or that intensity zone where fat can be used. Once again, 60 to 65% of your VO2 max, maybe your heart rate, is optimal for fat oxidation. That is about the highest. Granted, you could run at 60%, right, and you're just cruising along in your 10K run or whatever, and you're about to finish, and then you get that kick where you can run really fast. Well, that kick comes from the stored ATP. It's not like the fat all of a sudden can give you a heart rate of 80. You've got stored ATP, so you can use that, and as your heart rate goes up for just a little bit. So, but consistently over time, it's about 60% of your max heart rate or VO2 max. When we train in that zone using fat, so let's say you're trying to lose calories from fat, you're trying to diet, or just try to burn fat, we can get more efficient in doing that. So if you look at marathon runners, they spend a lot of time in fat oxidation before they can eat, because there's such high intensity. They burn through their carbs so fast. That's why they're super thin. I mean, there's just no other way around it. We can, by doing that, by training that, we can increase mitochondria. So we're producing more ATP. We can increase oxidative enzymes that help us do aerobic work, so long distance endurance work. We get more capillaries in and around those muscles, so we can feed more oxygen to them. And then we increase concentrations that allow fatty acids to be uptaked. That's the FAB and the CPT. So don't worry about FAB and CPT. Just know that there are hormones and enzymes and carrier proteins that help get those fatty acids into the Krebs cycle. So we can become more efficient with fat. And that's fine if you're not interested in necessarily winning a race, but doing something for a very, very long time, like hiking the Grand Canyon rim to rim and then maybe going back again. That would be really good to train this zone, because that might be the only fuel you get. So something like that. Okay, if you chronically eat fat, you will utilize fat as your fuel source. So if you are habitually eating fatty foods, your body will then kind of start to convert to using that more as a fuel. Not a great idea. Obviously, fat's not really good for your cardiovascular system. So, we don't want to have strokes and heart attacks. So you probably don't want to train it that way. The opposite is also true. If we start limiting fat from our diets and eating better fats and less of them, then the opposite is true. We become less reliant on them. Stored fat has about 50 times the energy potential than glycogen, right? Because it's almost 9, it's 9.4 if you look at the decimals, but it's 9 calories per gram, and we're only getting 4 out of carbs. So of course it's twice as good, right? So, but once again, it can only be utilized at about 60% of our max effort. So there's more of it, but we're not going to get the output that we want. Fasting does not increase performance, but it is a good way to utilize fat, right? Because fasting means we're not putting anything in our mouth, so we're relying on the stored fat. Once liver is depleted, you're gonna get more calories. You're gonna burn more calories from fat, and that's fine. But realize that it's gonna change the pH of your blood a little bit, and you can go into something called ketosis. So that should be ketones, one word, by the way. So you go into something called ketosis, and that's not necessarily good for your brain or for your body. So it makes you really sore and not feel good. Yeah, the keto diet is basically this, right? And yeah, you're gonna lose weight, but you're gonna feel really, really bad. So those who have been on keto, you might know. If you did it hardcore, you didn't feel very good. Little evidence shows that fat is good, and there's so many side effects, and we don't want to use fat as our primary fuel. So we've got different things that'll help burn fat. Caffeine is one of them. The question in your test will be there. So caffeine is probably the easiest one to remember, but here are some others, and you can stack these and put them in a bottle and sell them. So you might find it. Some of you are wondering about, I get questions all the time about pre-workout. Yeah, that's a fat oxidator, basically. It's a stimulant, and then it's got a bunch of other stuff in it. That's what you're into. But you can see there's a big market for this stuff. We find things that increase fat metabolism, and we like to put it in bottles for people. So here are your terms. Just understand there's 2 forms of carb loading. Understand that exogenous food is anything you're eating during your race or an event or your activity, and that you better be mindful of the glycemic index of those exogenous carbohydrates so that you put what you need in you at the right time. And lipolysis is fat, breakdown of fat, and then fat oxidation is the use of that fat as a fuel source. Okay, you guys, we did it. I hope I didn't go too fast. Once again, I just kind of like to do a quick overview. I'm hoping you've already read through the slides, and maybe this answers a few questions. If it doesn't answer all your questions, please text, email me, and I'll get back to you. Thank you.